Hello everyone, my name is Choi from South Korea and I'm currently working as a postdoctoral researcher at Korea Institute of Science and Technology. The topic of today's presentation is distance-based formation control with goal assignment for global static stability of multi-robot systems. I've divided my presentation into three sections. Firstly, I'm going to introduce our research background and limitation of previous approaches. Secondly, I'm going to talk about our main research work and then I will show some simulation and experiment results. In general, there are three approaches for formation control of multi-robot systems. First one is the position-based control. In this approach, the goal is given by a global position and so each robot should know its global position. Therefore, this approach cannot be used when the global coordinate is not available, like GPS denied environment. For the local coordinate systems, we can use these two approaches. In displacement-based control, the goal position is given by the relative position from its neighbor robot. In distance-based control, the goal position is determined by the inter-agent distances from neighbors. When we use the displacement-based control approach, the local coordinate of robots should be aligned, which means that all robots should share a common coordinate. However, it's not easy to share the common coordinate when only the vision and LiDAR sensor are equipped without network communication. Besides, there exists an error measuring the direction of nodes, which could be a common coordinate due to the uncertainty of the compass sensor or the environment. On the contrary, the distance-based control approach doesn't need an aligned local coordinate system. In this paper, we focus on this approach. The conventional distance-based control approaches are suffered from the global asymptotic stability. Generally, the controller in this approach is designed based on the gradient method. However, depending on the initial positions, robots converge to not only the desired formation, but also converge to the undesired formations. Here, the undesired formations are derived from the local minima of the closed system. Therefore, global asymptotic stability is a challenging issue in distance-based formation control. There have been several attempts to handle this issue. Some research just focus on the local stability, and other research add angle constraint on the desired formation to get the global stability. Recently, there was an approach achieving the global static stability by extending the dimension of the desired formation. However, this approach is restricted to the complete graph-based target formation, which is somewhat unpractical when a large number of robots are deployed. On the other hand, goal assignment is an important thing in formation control because if we can assign a proper goal for each robot, we can increase the conversion speed to the desired formation, and also we can reduce the possibility of collision. However, the existing goal assignment strategies are limited to the position-based formation control framework, and they did not consider the underactuated property of robots. So our proposition is to develop a new goal assignment strategy for distance-based formation control. There are two contributions of our work. First thing is we can guarantee the global stability using the goal assignment strategy. And the second thing is that we consider the underactuated mobile robots. Let's move on to the main section. Before showing our main work, we are going to see some preliminaries. In this paper, for the presentation of interactions among robots, we used graph theory and graph rigidity. A framework F is defined as a pair of graph and positions of robots. Using the relative positions among robots, rigidity function is defined. By differentiating it, you can define the rigidity matrix like this. Using the rigidity function, we can figure out which framework is rigid or not. Since it's not easy to understand from this definition, let's see the following example. The first framework is called a flexible framework because we can deform it continuously. Differently, the other two frameworks are rigid. However, the second one is locally rigid because we can flip over this framework along this line. The control objective of this paper is to drive robot to converge it to the desired formation, which is isomorphic to the target framework F star. Here, the isomorphic means that it allows the rotation, reflection, and translation of F star. The first main result of this paper is organized by the following theorem. The closed signals are bounded if the forward velocity vi and the angular velocity wi are chosen as follows. Let's see the proof of this theorem briefly. The epsilon function v is chosen like this. If we apply the controllers, we have v dot like this. At this moment, we apply Barber's lemma, and then we can obtain that v dot converges to 0. Consequently, there exist two equilibrium sets epsilon star and epsilon. Epsilon star indicates the desired formation and epsilon contains the undesired formations. Unfortunately, we cannot guarantee that the robots converge to the epsilon star. So, we need a solution to prevent robots from converging to epsilon. We thought that goal assignment might be helpful for this problem, and thus, we developed a new goal assignment algorithm. The main procedure of this algorithm is composed of 3 steps. The first step, we select two robots, agent A, agent B, and the next step is to compute the error under the current goals Z cur and the error under the exchanged goals G new. And the final step is to exchange their goals if this condition is satisfied. Let's see the example on the right side. Assume that the current target formation is given like the upper figure. Now we select agent 1 and agent 4. Then using the formula on the left side, we can compute Z cur and Z new. If Z cur is bigger than Z new, the goals of agent 1 and agent 4 are exchanged. And then the target formation becomes like the lower figure. The main result of this paper is given by the following theorem. If the goal assignment is executed, the global asymptotic convergence to the target formation is accomplished. Let's see the proof of this theorem. According to the definition of Z cur and Z new, we can rewrite the Lyapunov function like this. If the goal exchange happens at Tk, we have this inequality. Therefore, we can say that V decreases as the goals are exchanged. In conclusion, V is not stuck to local minima and converges to 0, which means that the robots converge to only the desired formation. To validate the proposed approach, we conducted simulation and experiment. For the simulation, the target framework, initial conditions, and design parameters are chosen as shown in this slide. This slide shows the formation result without the goal assignment and with the goal assignment algorithm. Let's see this video. At this moment, as you can see, the goals of agent 1 and agent 4 are exchanged in the right video. Then we can see that the target formation is achieved when the goal assignment algorithm is employed. In these figures, the upper and lower part represent the equilibrium set epsilon and epsilon star. As you can see in the left figure, the error Z did not converge to 0, while our transpose Z converges to 0. This means that the robots are stuck to local minima. On the other hand, in the right figure, the goal exchange happens at this time and then Z converges to 0. Therefore, we can say that the goal assignment algorithm helps robots to converge to the target formation. Now, let's see the experimental result. We consider 5 mobile robots and a PC as a server. Note that the initial conditions are different from the simulation, and we employ collision avoidance mechanism to avoid the unexpected collisions among robots. Let's see this video. As shown in the right video, the robots converge to the target formation with the goal assignment strategy, but the robots in the left video did not converge to the target formation. Moreover, it takes much longer time to converge because the avoidance mechanism is activated. From this video, we can say that the proposed goal assignment algorithm helps to avoid collisions as well as to converge to the target formation. In the left figure, Z is subject to chattering phenomena because of the collision avoidance, and it didn't converge to 0. However, as shown in the right figure, Z converges to 0 without the chattering phenomena because goal exchange happens 2 times. Now, let's end my presentation by concluding our work. New goal assignment strategy for distance-based formation control has been developed, and it has been proved that the global stability is achieved under the proposed goal assignment algorithm. And numerical and experimental results have validated the proposed theoretical result. That's all I have to say, and thank you for listening to my presentation. Thank you.